Okay, Professor Deskins here, and I wanted to make a video about reactors. So we're not really going to get too much into reactors in the course. Take reactor design or other classes, but since it's an important part of kinetics and catalysis, it's something that we should at least touch on and discuss briefly. So let me just discuss the different types of reactors and how they relate to what we're going to talk about in class and how they relate to kinetics and so forth. So, you first simplest reactor is the batch reactor. And in a batch reactor, we have some sort of tank or some sort of volume or vessel where we start a reaction at a certain time, we let the reaction go for a while, and then we may stop the reaction at some point and then remove the products out of our reactor. And that's pretty much it. It's the simplest reactor out there. It's a common laboratory reactor because it's so simple. It's a common laboratory reactor. It's also easy to analyze, I would say, compared to other reactors. Straightforward. The underlying equation that we need to be aware of is dC, and I'm just saying this is concentration of species A, and it's really concentration of other species. dCB dt is equal to RB, etc. The concentration profile within the reactor is just equal to the reaction rate. So if we know the reaction rate, which we can get from the mechanism or from measuring or whatnot, we can identify the concentration of different species as they change with time. And because of that, you should be aware that this is not steady state. So the concentration of different species are changing with time. So it's a transient process. The concentration at one time will be one value, at a different time will be a different value. That's the batch reactor. The most simplified batch reactor, we just assume that it's uniform concentration, and this is again a higher topic for reactor design, but if there's concentration gradients within our reactor, that can change how the reaction rate is in the reactor and how our analysis proceeds. But for the most part, we'll assume if it's well mixed, it's the uniform concentration, and we can simply determine reaction rates based on changes in concentration using these equations right here. So that's the batch reactor. Let me go ahead and talk about the second type of reactor, and that is the continuous stirred tank reactor, or Cstr. It's sometimes referred to as Cstr. So our Cstr or Cstr reactor. So the idea is we have some tank, and this tank has a certain volume. The reaction takes place within the volume. We have a flow rate, and we have a concentration. I'm just going to call this A for the feed and CA exit. So we have the concentration of A in the feed and the concentration of A in the exit. So it goes in there, it reacts. This is assume that it's uniform. So just like the batch reactor, uniform concentration within the reactor. I mean, and all this reactor really is just a batch reactor with a feed and a outlet stream in it. So it's just a branch off of that. The other thing that separates it from the batch reactor is that we want usually run at steady state. And so the concentration coming out of the reactor is constant with time. And so that's a difference between the batch reactor. The underlying equations, well, if we just do a material balance on this, and in this case I'm just going to call this V dot, this is the volumetric flow rate, times the concentration of A feed, So those two are multiplied. So this right here is number of moles of A is equal to the rate of A consumption or generation times the volume of the reactor is equal to V dot CAE. So basically it just says what the amount of A going in, and this should be a plus, big mistake, plus, not equal. The amount of A, let's just erase that so it's clear. The amount of A going in plus the amount of A reacted, which could be a consumption or generation, is equal to the amount of A leaving. And that's just our material balance. And we can simply go ahead and rewrite this here to CAF minus CAE is equal to negative RA V over V dot. So just taking this equation, rearranging it, and that's equal to negative RA times this value here, this theta here, which is the average residence time. And so we talk about the residence time of a Cstr reactor, and that's basically telling us how long is the reactor or the species within the reaction vessel. And so this is the type of equation that we could use to analyze it. So if we knew RA or RB or whatever, we could go ahead and do the analysis on the feeds concentrations and the exit concentrations and so forth, and do our analysis of reaction rate and so forth, just like we've done with previous analysis. So now let's talk about the last type of. The last reactor, if you haven't recalled by now, is the plug flow or tubular reactor. Tubular. And I'm just not spelling so good today. Tubular reactor. And in this case we have some tube, stuff coming in, stuff coming out, and we have ideally steady state. We want it to be well mixed and radially. So what I mean is we want it well mixed, in this direction here. The concentration will be changing with time, or not with time, but changing with length along the reactor. So if species A is coming in here and it starts to react, the concentration may go down, down, down as we go further along the reactor, but we don't want the concentration to deviate along the radial direction. And again, if we go ahead and write out our equations here, and I'm just going to define a little segment here as delta V, so some change or some segment of the volume. So we can have the volumetric flow rate times CA V plus R delta V is equal to Q, oh, excuse me, not Q, V dot times CA V plus delta V. So basically we're doing a material balance on this little segment here. So we're saying that there's some amount of A coming in here, some amount of A leaving this little segment, and then within this little slice here there's a reaction taking place, and that's exactly what this reaction is saying. What's coming into that little segment plus what's reacting in that delta V, and then what's leaving at that little delta V, that little slice there. So if we go ahead and do this, and if you remember back in calculus and all that, we'll let delta V approach 0, and so that lets us go to a simplified equation, d times the derivative of V dot times CA dV is equal to the reaction rate. And so that's our equation that we can again relate to our reaction rate to the specifics of our reactor. Now if V dot is constant, then this equation simplifies a little more, and if that's the case, then dc, we can take out V dot out of there, and dCA d theta is equal to RA, where theta is equal to, again, that's our residence time, and that's V over V dot. So just like we had with our continuous stir tank reactor, we have a residence time for a plug flow reactor. And again, for the kinetics analysis, we've really mostly focused on batch reactors. All these different type of reactors have their different advantages. The plug flow reactor is great if you're doing, if you have an industrial reaction within a factory and you want it to run under steady state conditions. That's great. You know, batch reactor, the disadvantage is you have to load in your reactants, run the reaction, remove your products, and so forth. So it's a little more complicated. But the big advantage of the batch reactor is we don't have, the analysis is very straightforward. With the plug flow and the Cstr, we have to worry about keeping it well mixed within the radial direction, for instance, or well mixed in certain directions. We have to worry about the effect of residence time. With the batch reactor, we don't have to worry about any of those difficulties, so it's often used for experimental or laboratory analysis. So again, just wanted to close with that and give you a little review of reactors. That's almost about as much as, probably about as much as we're going to talk about in the class, but there you go. So have a good day.